Good morning students. I am going to discuss this mathematical modeling of power hydraulic systems. This reference book is the same, that is the textbook I referred earlier, that is the textbook authored by Katsuhiko Ogata. Okay. So, before going to the hydraulic servo system, let me discuss something about this power hydraulics. Actually, except for low pressure pneumatic controllers, these compressed airs are seldom used in case of high pressure systems and also for precision control. Generally, these hydraulic systems are used, hydraulic power systems or servo systems are used when the application demands precision control, accuracy, and this heavy load maneuvering. So, all these cases, this widespread use of power hydraulic system in aircraft system, rocket launchers, and robotics. There are other applications where high power requirements is very important. So, there we use generally hydraulic servo systems, hydraulic power amplifier. So, this there are generally these hydraulic power hydraulics are used along with these electronic controllers, because in such a case these advantages of both electronic controllers as well as hydraulic power can be combined. Okay. So, generally this it is actually used for fast response and for speed reversal and also accurate control, I have told earlier. So, this maximum pressure in the hydraulic power systems can go up to 700 bar or 70 megapascal. Okay, but that is the extreme case. Usually we keep the maximum pressure, we prefer the maximum pressure in hydraulic systems within 350 MPa or 350 bar or 35 MPa. So, such a high pressure can be maneuvered by using such a very high power systems, can be used this hydraulic by means of this hydraulic pressure. So, which actually originates from the Pascal's law, which all of you knows. All of you know it is very beginning of that power systems, that is the underlying concept is the Pascal's law. Okay. So, in this particular figure you can it is displayed this hydraulic servo system. This hydraulic servo system or hydraulic servo motor, it is essentially a pilot valve controlled hydraulic power amplifier and actuator. The pilot valve is a balanced valve in the sense that the pressure forces acting on it are all balanced. You can see here, this is the pilot valve. Okay. So, this is the balanced valve, this is called the pilot valve, and this is the power piston and power cylinder. This is the power piston and this is the power cylinder. And this is the load which is acting here. So, it is actually heavy load. Okay. So, this pilot valve is a balanced valve in the sense that the pressure forces acting on it are all balanced. A very large power output can be controlled by a pilot valve, which can be positioned with a little power. That is why it is called pilot. So, you have to apply little power, but it will control a large amount of load. So, that is why it is called pilot operation. Okay. So, this particular system is also termed as servo system. Now, in this figure, this is the simplified model of this power system, hydraulic servo system. So, you can see here this pilot valve. In this pilot valve, this is actually there are 4 ports and 2 positions. So, this is called the this pilot valve is 4/2 direction control valve. Okay, why 4? Because there are 4 ways or 4 ports and 2 positions. 4 ports means one port is connected to this one. This is one port connected to this pressure source, that is oil under pressure. So oil will come to here, and these 2 ports are connected to drain. So actually these are not 2 ports. All these ports are connected to the same drain actually. So this is also going to drain, and this is also going to drain. So actually these 2 ports are connected somewhere in a common port, and then it will move to the drain. So that is actually the concept. So these 2 ports are generally termed as second port, that is connected to drain. So another port is here, that is port number 1. You can see here, this is the third port, this is the 4th port. So there are 1, 2, 3, 4. So drain port is common, although you can see these 2 different lines, but these 2 different lines are combined after some time. So this is considered as a single port. So 1, 2, 3, 4, total 4 ports and 2 positions. 2 positions means it can be positioned in 2 ways. If you just shift it to here, see this will be shifted like this. So in this position, this fluid will come through this particular path. This path will be uncovered. Okay. So let me delete this path. So this I hope you have understood, 4 port and 2 position. Okay, now there are some assumptions. That is, first assumption is negligibly small load mass. That means there is no load mass is given. So negligibly small load mass. Negligibly small load mass is considered in this current figure, actually we are discussing only the integral controller. So with this arrangement, with this particular assumptions, this hydraulic servo system can be designed as the integral controller. So this is one assumption, that is negligibly small mass. Okay, another is this inertia of piston is not considered. Okay. So such a servo motor constitutes the servo motor, servo actuators, all are basically termed as the same thing. Okay, this is actually uttered in the same breath. So hydraulic system, power hydraulic systems, oil hydraulic systems, those are actually synonyms. This power hydraulic and this hydraulic servo motor system. This is actually hydraulic servo motor or hydraulic servo actuator. So these are all synonymous. You can term it hydraulic servo actuator also, or hydraulic servo motor. So such a servo motor constitutes the basis of the hydraulic control circuit. So in the hydraulic servo motor, this pilot valve has 2 lands on the spool. So this is called the spool, and see, this is the spool here, and these are 2 lands. This is one land and land. Similarly, this is also land. These are 2 lands, okay, on the spool. So if the width of the land, see, this is the width of the land. So this width of the land is smaller than the port of the valve sleeve. See, this is the width of the port of the valve sleeve. If this width of the land is smaller than the width of the port of the valve sleeve, then it is called underlapped valve, then it is called underlapped valve. So, in contrast, if the width of the land is more than the width of the port of the valve sleeve, then it is called overlapped. Overlapped valve. Okay. Now, if the width of the land is same as the port width, then it is called is identical with this, then it is called zero lapped. So, there are three categories: number 1 underlapped, number 2 overlapped, number 3 zero lapped. For this zero lapped, we will consider in our analysis this zero lapped valve, because it is easy to describe this. This is actually simplest assumption. This will make the analysis simplified, because this will make the system perfectly linear, and different constitutive relations can be easily understood. So, actually in the practical scenario, underlapped or overlapped valve may exist, but this underlapped valve will increase the linearity, will improve the linearity, but it will aggravates this accuracy problem, whereas this overlapped valve will increase the non-linearity. So, it is actually difficult to analyze this overlapped valve. So, generally this for this prediction purpose, for estimation purpose, zero lapped assumptions are considered. So, we will consider the zero lapped valve, and along with this another assumption is, so number 3 assumption is zero lapped valve. So, these are all assumptions, important assumptions. Okay. So, another fourth assumption is that incompressible fluid flow, that fluid is incompressible. Otherwise, that means this rho is constant, this fluid density rho is constant. So, that is the meaning of incompressible fluid flow. So, let me complete this one. So, how it is becoming integral controller. So, let us see that thing. See, this operation is that when we are applying some displacement x to the spool of the piston, then this port 1 will be uncovered. So, it will be pushed in this direction. So, this port 1 will be uncovered. So, and this port 2 will also be, this will be, whole thing will be shipped. So, let me show it in the red. So, it will take this position. Okay. So, in this position you can see this oil under pressure, this this oil, pressurized oil is allowed to flow through this path, because this port 2 is uncovered when it is shifted to the right side. So, fluid is coming to this direction and it is applying pressure to this particular power piston. So, this is connected, generally connected to a higher load, but here it is considered to be negligible load. So, now this fluid is pressurized oil is applied, pressurized this fluid pressure is applied, fluid pressure force is applied at this side of the piston, whereas this side, fluid at this side, oil at this side is connected to the drain side, because this is uncovered. See here, this pressurized fluid can flow only in this direction, but it is not allowed to flow in this other direction, because this particular land will offer some resistance will not allow this fluid to flow in this particular direction. So, this direction fluid flow is not permissible, only fluid will flow in this particular direction, and fluid in this particular side of this power piston, this is connected to the drain line. So, this fluid is connected to the drain line, and this drain line is generally connected to the oil tank. So, that is at the atmospheric pressure. So, this is your high pressure, this is the atmospheric pressure. So, therefore, this side pressure is very less, this side pressure is atmospheric pressure, and this side pressure is this oil pressure, that is the high pressure. So, there is some pressure difference, pH delta P equal to high pressure minus atmospheric pressure. This atmospheric pressure is very close to 0. Generally, we take this atmospheric pressure as the reference pressure. So, then this pH, that is the high pressure, it is actually termed as gauge pressure. So, this delta P is acting here, this delta P multiplied by this area. So, that is the pressure force acting on this particular power piston, and this piston area is very high compared to this area. So, this force is basically magnified. This is according to the Pascal's law. Okay. So, now let us establish these equations that for this come to the again our original topic, that is how it is becoming integral controller. So, let me discuss this. So, now let that rate of flow of oil is Q kg per second, mass flow rate of the oil. Okay. So, this A rho, this is the A area, and this density is rho, density of the oil is rho. So, this distance, when it is clear that when x is acting here, y will be acting in the opposite direction, because pressure force is acting here. So, now this A rho, we can write this A rho, forget about rho, A multiplied by dy, that is infinitesimal A into d rho dy, that is at time dt, this displacement of this piston is dy. So, A dy is the volume change. So, multiplied by rho, that is the mass flow, change of mass of the oil. So, that can be equal to q into dt. So, if this dy displacement happens in infinitesimal time dt, then q is the kg per second, this multiplied by dt. So, this is the net oil flow here, and due to this displacement dy here, this dy multiplied by A, this is the volume change multiplied by rho, this volume change, that is the change of mass per change of the mass in time dt. So, that is equal to q dt. So, this is one equation. So, now because of the assumptions of underlapped valve, but because of the assumption of zero lapped valve, this q is, this flow rate q is proportional to this x. So, that is linear relationship is established, that is it is equal to k1 into x. K1 is the constant of proportionality, q is proportional to x. So, this is written as, so from this first equation, this A rho dy dt equal to q, that means k1 x. So, it is possible to write this particular relationship because of the assumptions zero lapped valve. Okay. And since this rho, it is multiplied by this rho straightforward because of the assumptions that this fluid is incompressible. So, this k1 into x. So, that means this if you take this Laplace transform, so A rho s y s equal to k1 x s. So, that means y s divided by xs equal to k1 by s a rho equal to k by s, where k equal to k1 by a rho. A and rho are constants, so this is actually k1 by a rho is also other constant, that is k. Now, clearly this relationship ys by xs, y is the output and x is the input. Here also this is the input in the pilot valve, and you are getting output here. So, this output by input, that is the equal to k by s, Laplace transform of output by input equal to k by s. Clearly it is the integral controller. Okay. So, this particular arrangement will serve as integral controller. So, next I am going to discuss hydraulic proportional controller. So, for this hydraulic proportional controller, we have to make a subtle change in the earlier arrangement, that is this particular link. This is actually floating link, it is not fixed anywhere, that is the floating link. Okay, this earlier figure is modified by inserting this type of link. This is also called feedback link. This is also called feedback link, other name, because its job is to give the feedback. Okay. So, this left hand side of this pilot valve spool is connected at this point B, okay, and this link is A, B, C, and this C point is connected at the end of the power piston. Now, here also this same thing, this when it is moved in this right side direction, this port is open. So, fluid will coming to here, this is fluid will acting here, and then this is, there is no change in the earlier conception. So, in this case, this let us I have already discussed about this floating link, how the dynamics will change because of the insertion of this feedback link. So, that means this particular thing will be happen, that is this xs equal to, this is actually there are two this superposition of this linear system will be, this is your E, superposition is applied here. So, this is your x, this is your E. So, this plus, so because of this feedback link, it is moving to this direction, this is your y, and sorry, this x, and there will be some x here. So, now because of this movement, feedback movement, so this plus this, that means x equal to, this is your b, this is your a. So, this x equal to this b by a plus b into E minus of this x, this x1 and x2. So, this is your x1 minus x2, that means this is your a, and this part is b. So, minus a by a plus b into y. So, this has been happened here, this summation junction, this b by a plus b into es minus a by a plus b into ys. So, that is subtracted here. So, you are getting xs here, and this x, as soon as, actually this is, in this case this is the input, E is the input. In the earlier case, let me come here, In this earlier case, this was the input, but here this input has been changed to this E. So, this is the input now, and if x is the input, y is the output in the earlier case, then what is the relationship? That was ys, look at this here, this ys equal to k by s. So, ys equal to k by s into xs. So, xs multiplied by k by s is ys. So, that has been done here. Ys equal to k by s into xs. So, ys is obtained here. There, after that this structure is obtained from this concept. So, now using this one, using this block diagram, we can find that ys by this output by input, in this case output from the system is y. So, ys by es, this can be written as directly from the block diagram. See, this is actually G, this is H. So, for this particular concentrate on this only. So, that is G by 1 plus GH, closed loop transfer function. This multiplied by this B by A plus B. So, that means this B by A plus B, this will remain as it is. G will be replaced by K by S, 1 plus K by S, and H will be replaced by A by A plus B. So, that means this is your B by A plus B into K by S divided by 1 plus K by S to A by A plus B. Generally, this term is much higher than this 1. So, 1 can be neglected with respect to this higher term. So, now this can be approximately equal to this A by A plus B, here B by A plus B. So, B by A and this K by S, this term will be cancelled out, this term will be cancelled out. So, this is approximate to B by A. So, this B is constant, A is constant. So, it is actually Kp, that means proportional gain. So, this output is proportional to input. So, this is actually proportional gain. Here this gain, proportional gain can be adjusted by effectively changing the lever ratio B by A. This adjusting mechanism is not shown in this figure. But there is provision of changing this lever ratio B by A. So, this is about hydraulic proportional controller. So, next I am going to discuss this hydraulic proportional plus integral control action. Now, before discussing that PI control action, proportional plus integral control, we need to revisit the concept of dashpot or damper. So, here you can see this is the schematic diagram of damper or dashpot. So, look at this figure at this moment. So, this is attached with this is mounted on a solid structure, solid foundation with, and this is the spring K here. So, that if some force will be, if some displacement will be given, that is y displacement is given here to the piston, this is the power piston, this is the cylinder. If you give this displacement y to the dashpot piston, then there will be change, momentarily change of the displacement of this one. See, this cylinder is not fixed, the spring is fixed and on the other side, and the cylinder is attached to the spring at one end. So, when you are giving some displacement y, this point, this end point of the cylinder will also experience some displacement z which is equal to y. But as time proceeds, then there will be some spring force acting here, that is the restoring force of the spring. So, spring force, due to spring force acting at this particular side, this cylinder will be displaced to this side. So, why this cylinder will be displaced? Because of this pressure, this P1 is higher. If the spring force is applied, you are giving this displacement y in this direction, due to which this spring force, restoration force is applied here, that will increase this pressure P1 with respect to P2. So, there will be some pressure differential, that is P1 minus P2. P1 is greater than P2 in this case. So, due to this pressure differential, this fluid, some fluid will flow through this restrictor R in this other direction, that is actually this flow rate with this flow rate Q, small q. This small q will be equal to this delta P divided by resistor R. So, some fluid will be flowing to this side. So, because of this fluid will be flowing through this path, so this cylinder will retain its original position gradually. So, that is shown here. See, this step change of y is given in this direction. This is the step change of this y. So, due to which z will be momentarily changed, it will be z, this displacement of the cylinder will respond to y immediately, but as time proceeds, this z will be decreased to the 0 value. So, cylinder will attain this 0 position, this original position. Note that piston will not come to this original position, piston will be displaced, but this z will be taking some original position, will be retaining this original position after some time. So, z response is this, and this y, this is the piston position, will be remain this y. So, this is the y after this considerably high time of t, but here you can see z is diminished to 0. So, this can be written like this. This constitutive relations is that A into area is the, look at this area of the piston, area into P1 minus P2. This is the force acting here, acting at this particular pressure force, acting at this particular piston. The same force is acting here also according to Pascal's law. So, this is the same force, this A P1 minus P2. This force is balanced by this K into Z. Z is the displacement. Because of this spring displacement, spring will apply some force here. So, this force, this pressure force and this pressure force are balanced. So, that is why you can write this relationship. So, K is the spring constant and A is the piston area. So, this flow rate Q equal to, I am once again writing this Q equal to P1 minus P2 divided by R. Okay. Another equation is Q dt, that is similar to the earlier discussion, that is A rho into displacement. Now, see here displacement is dy at this infinitesimal time dt, we have to consider infinitesimal time dt, this is the dy and this is the dz. Now, this dz is considered, dy is considered to be greater than dz. So, this net displacement is dy minus dz. So, this is the volume change, this A into dy minus dz, this is the volume change because of this movement of this power, movement of this piston, dashpot piston and cylinder. So, this is the volume change, that multiplied by rho, that is the mass change, change of fluid mass, and that is happening in infinitesimal time dt. So, this q dt will be equated with that. So, this is the three relationship. Again here rho is constant. So, from this three relationship you can write from this last relation dy dt, that means minus dz dt equal to q by a rho. So, that means this q means P1 minus P2 by a rho. P1 minus P2 means kz by a. So, kz by a means a square rho. So another thing we have we are missing, that is P1 minus P2 by R. So this R is coming here, R is coming here. So next, in the next step you can write this dy dt equal to dz dt plus kz by r square a rho. So taking Laplace transform s y s equal to s z s plus k by r s square here it is r is square rho, r is square rho zs. So now this transfer function here, this output is y, this is the input, this is the output. So y is the input and z is the output. So output by input, input is y, which is equal to s by s plus k by r s square rho. So this is equal to, now this particular, look at this particular expression, this if you can perform this dimensional analysis, then you will find that r s square rho by k, this is having the dimension of time, that is second. So this is actually r s square rho by k, this is actually is time constant t. So let us say this is t. So now this is actually s by s plus 1 by t. That means this is equal to s t by t s plus 1, or you can write express in this way 1 by 1 plus 1 by t s by dividing s in the numerator and denominator side. So this is actually, if you look at this form 1 by 1 plus t s, that means you can represent this particular transfer function by using this particular block diagram. See here, this is your unit t, this open loop transfer function, feed forward transfer function is 1, that is g equal to 1 and h equal to, from here it is actually, you can compare this cs by rs equal to g by 1 plus gh, where g equal to 1, so 1 by 1 plus h. So that means if g equal to 1, here g equal to 1 you have considered, and h is coming to the feedback loop, that is 1 by ts. So it can be represented like this, where t is the time constant. Okay, so this can be effectively represented by means of this block diagram. So now come to this hydraulic proportional plus integral control action. So for this hydraulic proportional plus integral control action, we have made this arrangement. See, this feedback link is attached to a spring which is connected to the ground, which is communicated with the ground. Okay. Now this dashpot is a floating member, it is not connected. This is actually power, this is the piston, power piston, the spool of the power piston, one end of the spool of the power piston is connected to the dashpot, and other end there is a fluid here. Okay. And fluid is all over, fluid is filled in all the sides. Okay. Now this note that particular arrangement, this particular power piston spool is having rods at these two ends. The same rod, it is actually having through rods, and here it is connected at this only one end only, it is in this dashpot, this spool is connected, spool rod is connected at one side, other side is not connected. So, other side, this side is connected to here, just notice this arrangement. Okay. So, all other things are same. Now, this structure is obtained as before, this x s equal to, that means this x. Now, this E is the input here, E is the input as before. Now, what is x? X equal to as before b by a plus b into E minus a by a plus b into this displacement, that is z. Correct. So, that is actually taken care in this particular part. Now, this y s equal to k by s into x s, this y and this x, that is actually discussed earlier in the beginning. This is the very basic part. So, y s equal to k by s into x. Now, come to here, this y s, this is actually this displacement y is the displacement of this spool. So, this is actually dy in infinitesimal time, this is your dz as I have discussed earlier. So, now this relationship will hold true. So, this is actually relationship between zs and ys. So, this is connected here. So, from this block diagram you can find out ys by es as before, that is b by a plus b into k by s divided by 1 plus k a by a plus b t by t s plus 1. Look at this side. So, this is your T s by T s plus 1. So, it is your T s by T s plus 1. See here T s by T s plus 1. So, this is your k by s, T s by T s plus, this s will be cancelled out. Okay. So, again this portion is considerably high compared to this one. So, one can be neglected. So, this can be equated, almost equated to this Kp into 1 plus 1 by Tis, where this Kp is the lever ratio, this B by A, and this Ti is the integral time constant, that is equal to R A square rho by K. This will come if you replace all these things. So, this is nothing but time constant, Ti is the time constant of this system, R A square rho by K. It is having the dimension of this time, that is second. You can do this dimension analysis by using this MLT, mass, length, time. Then you will find this is having the dimension of time. So, that is all for proportional plus integral control action. So, next come to proportional plus derivative control action, PD. Okay, so, this is your hydraulic proportional plus derivative control. So, slightly different arrangement will make it to the proportional plus derivative control. So, in this case, what is the difference between this earlier construction, earlier design and this design? That is this current figure, you can see that this dashpot and this power piston is grounded, is mounted to the ground, whereas you can see earlier this is actually floating. Okay. So, there lies the difference between these two, and another difference is that this spool is through here, out here. So, this spool is through, only this spring is added in between this spool and this spool. That means, this displacement y and this displacement here is not same. This displacement at power piston are not same, or you can see this z and y are not same, because this is, what is the displacement here, the same displacement here, because this spool is through here and this pull is through here, because y is what is the y value of y or dy, that is the same here, but here this distance is changed because of this compliance of the spring. The spring is attached in between this y and z, because spring will be compressed or it will be under tension. So, that will make this displacement z and y different. So, that is the only difference with this particular arrangement. So, here let us write down this constitutive relation, that is force balance first. The spring constant is k. So, k into, let us say y is higher than z. So, that is actually happening because this is your input E, and this x, due to this input x will come here, and this y will be coming to here. This y is actually driving this particular system. So, necessarily this y will be greater than z. So, k into y minus z, this is the restoring force on the spring. So, that is equal to A into, because of this force acting in this direction, this pressure P2 will be higher than P1, because this is the tendency of this piston is moving to this side. So, that will compress this fluid, try to compress this, try to apply force on this fluid here, but fluid is incompressible. So, fluid the same volume which is compressed, which is reduced here due to this movement of this piston, this same volume of the fluid will pass through this resistor to this other side. So, again let us write one by one, that is this force. It is clear that P2 is greater than P1. So, A into P2 minus P1, this is the effective force acting here. So, A into P2 minus P1, that is acting in this side, and the spring force is acting in this side. So, this is actually balanced because spring is compressed. So, when spring is compressed, spring will apply force here as well as there. Spring will apply force here as well as there when the spring is compressed. So, now this is k into y into z, this spring force, that is equal to A P2 minus P1. So, another relationship is Q is P2 minus P1 divided by R. Another relationship is third relationship is Q dt rho A dz. Okay, this flow rate and this Q mass flow rate multiplied by dt. So, that is equal to A into dz. Dz is the displacement of this particular piston in this direction. So, this volume which is reduced in this chamber is A into dz. So, that is multiplied by rho. Sorry. So, these three constitutive relations. From these three constitutive relations, we can find out this y equal to, as before, z plus A by k by k q r A by k q r. So, that means this is equal to z plus r replacing q r a square, and here also this r a square rho divided by k dz dt. So, now after taking Laplace transform, so Zs by Ys equal to 1 by, this is again t, so it will be s, so this is your 1 by Ts plus 1. Okay. So, you can see now here 1 by Ts plus 1, this term is coming here. So, let me now find out this Ys, this is the output from the system and this is the input from the system. So, Ys by Es, let me make some room out here. So, Ys by Es equal to a b by a plus b from this block diagram. Now, coming to the block diagram, from this block diagram you can write is k by s divided by 1 plus a by a plus b k by s into 1 by T s plus 1. Okay. Now, again this term is much higher than 1. So, 1 can be neglected. So, this is 1 can be neglected. So, this can be simplified to Ys by Es equal to Kp into 1 plus Ts, where Kp equal to B by A lever ratio and T equal to R square rho by K. So, clearly this particular expression is similar to that of PD control action, proportional gain, and this is your derivative time constant. So, this design is the proportional plus derivative control action. So, next coming to the proportional plus integral plus derivative control action, that is PID control action. So, in this PID control action we have to combine these two designs. See here, this is actually PD portion, where these two, this one, this cylinder, power piston, power cylinder, as well as this dashpot are mounted to the ground, fixed to the ground, whereas this is floating. So, that means in this particular arrangement we have combined both the designs of proportional derivative as well as proportional integral controller, which we have discussed separately just now. Okay. So, that means you see here, this is actually these two dashpots are connected back to back. So, here these two dashpots are of different design. One is this through spool, another is this spool is connected at one end, another end is not connected. So, that is actually shown here separately, shown in this particular figure separately. So, here y is giving this displacement, y is the displacement coming to this side of this power piston, and that is affected to here also, here this, because this is the through spool. So, y will be here also, but displacement and at this point will be different than y because of the existence of this compliant element K2. So, let this displacement is W. Okay. This W is less than y. Okay. Now, this W is same as here, this W, but this displacement Z is different from this W because of this existence of this particular arrangement. Here this is not through, this spool is not through, because of that this Z is less than W. So, that is shown here, this Z is here, W is here. Now, see, because this y is higher and W is less than y, Z is still less than W, again Z is less than W. So, it is clear that this P1 is greater than P1 dash and P2 is greater than P2 dash. So, accordingly, let me write down this. Let us now try to find out this relationship between y and Z. That means, our target is to find out Ys, output is the Zs and input is the Ys for this particular system, So, Ys by Zs, Zs by Ys, this transfer function we need to find out. This is the transfer function for this system. Okay. So, then we will attach here, this part is already known. So, this part is also known, this relationship between x and y, that we will consider in the block diagram. So, this we are considering this system transfer function. Let us first derive the transfer function of this system. Okay. So, here this is shown separately. So, now let us quickly write down this relationship, that is K2 into y minus, this is the K2 into y minus W, that is equal to A into this force is coming to this piston as well as this piston. So, this is the force balance. So, I am writing A into, and we are considering this area of these two dashpot pistons are same, that is capital A. Here it is also A. So, A into P1 minus P1 dash plus A into, this is for this piston, and for this piston A into P2 minus P2 dash. So, another relationship can be written K1 into Z equal to A into, see here K1 into Z. So, this is the force acting here, restoring force. Spring, this spring is compressed, so it is applying force in this direction. So, K1 into Z, that is equal to this force acting to here. This force is acting to here also. So, that is your area into P1 minus P1 dash. This P1 minus P1 dash, this force is acting in this side. Here it is P1 into A1, here it is P1 dash into A. So, this resulting force is P1 A into P1 minus P1 dash, that is resulting force is acting and in this surface, and this force balance tells us that this K1Z equal to this, and this Q1, see this is your Q1 equal to P1 minus P1 dash divided by R. So, this is the three relationship from which we can write this K1Z equal to, from this second relation, this K1Z A P1 minus P1 dash is equal to Q1R. So, Q1R. So, next is Q1 dt equal to A into dW minus dz into rho. So, I hope you have understood, because this was discussed in detail in the previous examples. So, Q1 dt equal to this one. So, that means this W dot minus Z dot, W dot means dW dt, dz equal to dz dt is again Z dot. So, this is equal to Q1 by A rho. So, Q1 means this one, K1 Z. So, from this relationship you can write Q1 equal to K1 Z divided by AR. So, replace this Q1 to here. So, that means K1 Z K1 Z by AR divided by A rho, that is equal to K1 Z by A square R rho. So, you take this this A square R rho, this is actually a constant. So, let us now write down K1 Z by B, where B equal to this one. So, this taking Laplace transform now, S W S minus S Z S equal to K1 ZS by B. So, this ZS can be taken to this side, the right side of this equal sign. So, then you can write this WS equal to K1 by BS plus 1 into ZS. So, now for the right hand side, this is for the left hand side dashpot. Let us now consider right hand side dashpot. Similar equations can be written for this right hand side. That means Q2 dt equal to A rho dW and Q2 equal to P2 minus P2 dash divided by R. So, from this first relation, W dot equal to Q2 by A rho, that means Q2 means this one. So, A P2 minus P2 dash by Q2. In place of Q2 we are writing this one, P2 minus P1 by R. That means A R rho. Now, multiplying numerator and denominator by this A, it is A square. So, now A into P2 minus P2 dash equal to, this is again B, this same B. So, this is your B again. So, B into W dot. So, now come to this equation, let us say this equation number 1. Now, replacing this term A P2 minus P2 dash equal to B W dot and A P1 minus P1 dash, that is K1 Z. In this particular equation, we can substituting in 1 in equation 1, this K2 Y minus K2 W equal to K1 Z, this K1 Z, one substitution, plus A P2 minus P2 dash, that is B W dot. Okay. And then taking Laplace transform, this K2 Ys equal to K2 Ws, K2 Ws, and here Bs Ws. So, K2 plus Bs Ws plus K1 Zs. So, that means Ws equal to K1 plus Bs divided by Bs into Zs. this is actually not coming from here. So we have rewritten this equation, Ws equal to K1 plus Bs by Bs into Zs. So actually our target is to find out this input output relationship, that means what is Zs by Ys. So we are replacing this Ws in terms of Zs here, so that we can find out this relationship. So ultimately after replacing this, you will find this Zs by suitable substitutions, this Zs by Ys equal to T1s by T1 T2 s square plus T1 plus 2 T2 into s plus 1, where this T1 is equal to B by K1, T2 is equal to B by K2. Okay. So these are having some time constant, this T1 and T2. So this is actually final transfer function between this Z and Y. So this transfer function is used in this particular block diagram. See, this is the transfer function which we have derived corresponding to this particular arrangement. So this is your relationship between Z and Y. See, Z and Y. So this particular arrangement is represented by this transfer function, that is Z and Y. That is the relationship between Zs and Ys. Zs is the output, Ys is the input for this particular system, subsystem. So this is already understood, Ys and Xs, that is K by S, and this is also understood. Now find out this transfer function for the whole system. So that will represent this PID control action. So that is Ys by Es equal to B by A plus B into K by S. That is the same tricks. It is your this closed loop transfer function Cs by Rs. This is your Cs by Rs. This is your G, and this whole thing is H. So that formula is G by 1 plus GH, and that will be multiplied by this term B by A plus B. Correct? So in place of G we are writing this K by S and 1 plus GH, this into this. So these two are, this and this are in cascade, so these two can be multiplied. So 1 plus A by A plus, A by A plus B, K by S, T1s by T1 T2 s square plus T1 plus 2 T2 into s plus 1. So this is one term, this is another term, and this is another term. So again this one can be neglected with respect to this large term. So this can be equated to this Kp plus Ki by S plus Kds, where Kp is the proportional gain, Kp is equal to B by A. After simplification, neglecting this one with respect to this, you will find out this structure. So where Kp equal to this B by A into T1 plus 2 T2 divided by T1, proportional gain, all are constants. So this Ki equal to, here is the integral gain, this B by A into 1 by T1, and Kd equal to derivative gain B by A into T2. So, thus this design will represent this PID, proportional plus integral plus derivative control action. So let us stop here. So, thank you for your attention.